So today we're going to start the chapter on Laplace transforms. This chapter probably is completely new to most of you, but it's also one of the most interesting chapters in the course, and I think it's my favorite one compared to the other topics we cover. It's a very elegant method of dealing with differential equations, and extremely useful method in cases where the components of the differential equations are not nice functions. So for example, Laplace transform method in dealing with differential equations handles very well functions which are discontinuous, for example, which you will see later may happen in many applications. And even more general components than just classical functions, which makes the Laplace transform pretty much a required tool in those situations as well. We have to wait a little bit until we get the feeling of how to actually use Laplace transforms in solving differential equations, so we have to define the concept and focus on some of the most important properties. Although, if you look at the formulas generated from this concept, you will anticipate immediately actually how that concept, how the Laplace transform can be used to solve differential equations, linear differential equations to be more precise. Take your time to write this definition. I'm going to go over the definition a little bit before we handle a couple of examples. So a transform in the language of analysis essentially means a function of functions. So a procedure that takes a type of function and gives you a different type of functions with hopefully better properties. So the main idea is that, you know, I have the classical functions that I deal with in the context of the differential equation, and I use the transformation to associate a different class of functions, hopefully with better properties corresponding to the original ones. So the idea is to actually move solving the ODE in this different class of functions with hopefully better properties. So to fix the notation, essentially the Laplace transform takes a function f of t, t being, remember, the typical variable of a differential equation, and gives you a function denoted by big F of s. So that's a convention of notation. S is the variable of a different function. You can call that variable however you want, but to stick to the notation of a textbook, we call it S. And it's customary to denote this function using the capital letter of the original function. So the Laplace transform will associate a function called big F of s corresponding to a function small f of t. That's just the notation. So another notation is script L of f of t, or Laplace of f of t. Right? So remember, L, which stands for the Laplace transform, takes a function, gives you another function. How does it give you that other function? Well, it gives you this function via this integral. And I'll explain a little bit later, roughly speaking, why it's defined this way, although once you see the properties of this definition, you'll understand why this definition is useful. So the Laplace of f of t is defined as the integral from 0 to infinity of that function times e to the minus st dt. So once you do the integral, imagine you do this integral with respect to t, the answer would be an integral in terms of s. Now that's an improper integral, and we will always assume various properties on s, various bounds or limits on s that will ensure this integral exists, and also some assumptions on the function f of t. So we want to make sure, for this definition to make sense, we want to make sure that this integral is finite. So not only it exists, but it gives you an actual finite number, right? So not infinity or minus infinity. So that means not absolutely every function will have this property, this Laplace transform, but luckily, fortunately, most of the functions that are useful in practice do have this property. So they will follow the definition, and they will give us a finite integral. So let's actually write an example right away on how to find the Laplace transform for a very simple function. And then after that, we're going to just deal with table of formulas to find Laplace transforms, because this integral is not at all easy to find in practice. So that's why we have table of formulas for the Laplace transforms just like we do for example, derivative rules or integrals. So as an example, suppose I want to find the Laplace transform of an exponential, let's say e to the 2t. This is practically the easiest example to find the Laplace transform directly by the definition. So according to the definition, then this is going to be the integral from 0 to infinity e to the 2t times e to the minus st dt. Now focus on s, that this is a constant, right? So remember, t is your variable of integration, so we can combine these two exponentials and we have e to the power 2t minus st, and we can factor t. And this is just like the integrating e to the constant times t. Okay, so like e to the 5t. The integral will be e to the 5t over 5. 2 minus s is a constant with respect to t. All right, so the antiderivative then is going to be 1 over 2 minus s e to the 2 minus s t, evaluated between 0 and infinity. Now remember, from calculus 2, this is an improper integral, so when you plug in infinity, what you really mean is taking the limit as t goes to infinity of 1 over, or e to the 2 minus s times t over 2 minus s, and then minus 1 over 2 minus s e to the 0. Right? When you plug in 0 for t, you get e to the 0. So this is the part when you actually have to make some assumptions on s or on the function itself. Notice this is e to the t times a constant. Depending on the sign of that constant, you either have e to the infinity or e to the minus infinity. You want this integral to exist, so the only possibility for that to happen is to assume that 2 minus s is less than 0. That is to say, s is greater than 2. Because only in that case, your limit exists. So e to the minus infinity, remember, is 0. So that ensures this limit actually converges to 0. So I hope that makes sense. In practice, you don't have to worry about this. We will always assume that we have these imposed properties for that integral to exist. So we always assume that both the function and the bounds on s will satisfy the necessary conditions for that integral to exist. So that leaves us with 1 over s minus 2, right? If I bring in the minus inside over there, then we concluded that the Laplace transform of the exponential e to the 2t is 1 over s minus 2. Defined for s greater than 2, but as I said, for what we deal with in this class, we don't have to worry about explicitly mentioning that condition all the time. So as I said before, fortunately we don't do this by hand because we already have tables of formulas that have this Laplace transform computed for us already. For example, in the table, which you should have it in front of you, so table of Laplace transforms, you will see already this entry, the Laplace of e to the at is 1 over s minus a. Right? So if a is a constant, that's the formula. Of course, make sure you use it correctly. So if I want to use the table to find the Laplace of e to the minus 3t, a is minus 3, so to apply the formula correctly, I have a double negative here, s minus negative 3. So this will be 1 over s plus 3, the Laplace transform of e to the 3t. Here's another example from the table. The formula states L of t to the n, so the power of t is n factorial over t to the n plus 1, s to the n plus 1. So for example, if you have to find the Laplace of t to the power 3, that's identical to 3 factorial using the formula over s to the 3 plus 1. 3 factorial is 6 and 3 plus 1 is 4. So get used to use the table quite a lot from this point on. In fact, you need to make sure you practice quite a lot until you get the hang of it. it should be just as easy as using essentially differentiation rules, except you don't have to memorize them. You just look at the table and apply the corresponding formula. All right, so the next thing to talk about is perhaps the most important property of the Laplace transform, which is the so-called linearity property. So let me write it here. And this is important because of two reasons, first of all. Without this linearity property, we cannot actually solve linear ODEs with the Laplace transform. And another important reason is, in life, remember, we don't have an entry in the table for every function we deal with, right? So, I mean, functions typically are combinations of various entries like this. Like, for example, what if my function is t third plus 5 e to the minus 3t? How do I find the Laplace transform of this? So hopefully the linearity property allows us most of the time to be able to break down the function into entries in the table, in the linear combination of entries in the table, and then we could use the table for each of those components. So the linearity property states that the Laplace of a linear combination of functions, so let's say a f of t plus minus b g of t, is equal to a l f of t plus minus b l of g of t. So you could distribute the Laplace transform over a linear combination. So if I use the other notation with big F of s, the same property reads like this. So L of a f of t plus minus b g of t equals a big F of s plus minus b g of s. So you could distribute the Laplace transform over a sum or a difference or a linear combination of functions like this. This should not be a surprise to you, because if you remember the definition here, if I throw in a linear combination, we know the integral can be distributed over a sum or a difference of functions. So that allows me to do what I just mentioned before, taking the Laplace transform of combinations of these functions. So for example, what if I have to do, what if I have to compute L of 3 t squared minus 5 e to the, let's say, 2t. There is no entry for these formulas, but because of the linearity property, I can break it down into 3 L of t squared, so I can pull up the constants, minus 5 L of e to the 2t. So I could break it down like that, and then apply the formula for each of these entries. L of t squared, that's 2 factorial over s to the power 2 plus 1, minus 5 L of e to the 2t, look at the formula here, and that's going to be 1 over s minus 2. And then we can clean up a little bit the expressions here, so that's going to be 6 over s to the 3 minus 5 over s minus 2. And that'll be the Laplace transform of this function. So before we move on, let's define the so-called inverse Laplace transform, which is essentially going in reverse, starting from a function in S and then getting back to the original function. The reason we do that is because, as you'll see again later, you'll have to wait a little bit until we move on to the next lecture for everything to make sense. But the main idea is, okay, we start with an ODE, we move it to Laplace transforms and solve it with Laplace transforms, but then at the end we have to go back to the original function. So we have to have a way to go from the Laplace transform to the original. So that's nothing fancy, it's just a matter of saying, if I start with a function in S, which is the Laplace transform of f of t, then I can go backwards from big F of s to little f of t. So this is going backwards, essentially is taking the inverse Laplace. So just a little definition here, the inverse Laplace transform of a function big F of S is a function f of t such that, well, L of f of t is big F of S. So it's basically saying that you go in reverse, and the notation for this process is L inverse with -1 on the top, right? So the notation is L inverse of big F of S is little f of t. So to say that L of f of t is big F of S is the same thing as saying inverse of big F of S is little f of t. So these two are interchangeable. This second notation is via the original one. So one, again, very important aspect to mention here before we move on to other examples is that the linearity property also holds for the inverse Laplace. Because again, you will have the same situation. If you want to go from the inverse Laplace, for the Laplace to the original, you may have to break down that expression into entries in the table. Fortunately, the linearity property holds in that case as well. So it is true that we have L inverse of some combination of functions in S. We could distribute the inverse Laplace just like before. So we could distribute the inverse Laplace and then write this as the linear combination of the original functions. Okay, so L inverse of A big F plus B times big plus B big G of S is A f of t plus minus B G of t. With examples, this will make more sense, but again, the idea is you could pull up the constants just like you did it here, and then apply the table formula here. So in fact, let's end this part of the lecture with a very quick example. We're going to move on with slightly more difficult ones, but the idea is, like, let's say for instance you have L inverse of 5 over S minus 2 plus 7 over S plus 1. Let's see if we can fit this tiny example here. So via linearity property, this is equal to 5 inverse Laplace 1 over S minus 2 plus 7 inverse L of 1 over S plus 1. Okay, so 5 L inverse of 1 over S minus 2, 7 L inverse of 1 over S plus 1, now we recognize as being of this type. Okay, except we go from right to left. So 1 over S minus 2 goes into e to the 2t. 1 over S plus 1, that's like a minus 1, goes into e to the minus t. Okay, so therefore the answer here would be 5 e to the minus e to the 2t, and then plus 7 e to the minus t. So in my next part of the lecture, we're gonna basically move on with examples like this. So I'm gonna write down a bunch of formulas from the table, but you should have the table of formulas in front of you because it's easier to use it that way. And then we're gonna focus on slightly more complicated expressions when we need to do some algebra manipulations in order to use this linearity property, and then again break down the function into elementary pieces so you could use the table. So stay tuned for the second part.